Here is my next work-related problem. So here, very similar to the previous problem, we have a cable with mass 1/2 kilogram per meter is lifting a load of 150 kilograms that is initially at the bottom of a 50-meter shaft. So how much work is required to lift the load 1/4 of the way up the shaft? So notice that in this case, we do not want to lift it all the way up. We want to be able to lift it just 1/4 of the way up. So the setup of the problem is going to be very important, especially what your distances are. I think that's probably the most tricky part. But other than that, it's the same exact scenario as the other problem that we just did. So let's start off with the picture. So I have same thing, this bucket. Okay, so I have something and it has something inside of it, some load. I have this cable, okay, and I'm bringing it all the way up, and it's 50 meters. Okay, so it's 50 meters up. Okay, so now a couple of things to note is that now they didn't give us pounds, they actually gave us mass. So now is when we have to use this gravitational acceleration formula. Okay, so here the mass is equal to 150 kilograms of this load, and we are also told that the cable has a mass of 1/2 kilogram per meter. So let's first start off kind of how we did it with the other problem where we wanted to find the force, which was the weight. This time let's go ahead and we also still have two forces, but let's first start off by finding the mass, because we still have two forces. We have still the cable, and we also have the load of coal or whatever we're bringing up. But in this case, it's given to us in kilograms. So let's find the masses first. So let's find the mass of this and the mass of this. Okay, so for this one, the load, it might be a little bit easier to work with. So let's just start off with the load. So we know that the mass of the load is going to be equal to 150 kilograms, which is what were given to us. Okay, so that's 150 kilograms. So what will be the force in that case? Well, the force is equal to the mass times the gravitational acceleration, which is 150 kilograms times the gravitational acceleration, 9.8 meters per second squared. And what I'm going to get is 1,470 newtons. Okay, so that's the force required to lift up this amount of whatever it is. Okay, and then now we're looking for the cable. So now let's look at the cable. In this case, the cable, what do they give us? So they tell us that the mass is 1/2 kilogram per meter. Okay, so we want to find the mass of this thing. So right now we have 1/2 kilogram per meter. Well, that's not quite what we want, because if I were to take a small piece of this part, okay, so I'm going to take a small piece and I'm going to call this delta x. Well, we're going to do the same thing. Well, let's just imagine that this is 0, okay? And we're going to lift it 1/4 of the way up, okay? So let's just say that this is xi. So what's remaining is going to be 50 minus xi. Okay, so the mass right now that is given to us is 1/2 kilogram per meter. Okay, so that's what we're given. And now we're going to multiply this guy by the distance that's left. So it's going to be 50 minus xi. Okay. And if we were to distribute, then this is in meters, so the meters cancel out. So I'm left with kilograms. And what I'm left with is just 25 minus 0.5 xi. Okay, so that's our mass. Now we want to figure out what the force is going to be. So the force, or the weight, is going to be mass times gravitational acceleration. That's going to be 25 minus 0.5 xi multiplied by 9.8. And then I did this earlier. This is going to be equal to 245 minus 4.9 xi. Okay, so we have the mass, or the force required by the load, and the force required for the cable. Okay. All right, and now what we're going to do, let's go ahead and find the work. Okay, so the work in this case is going to be equal to the integral from A to B of the force due to the cable plus the force due to the load. Okay. So the integral from what to what? It's going to be from 0 all the way to how much? So how far do we want to take this? Well, we want to take this a fourth of the way up. So it's a fourth of whatever 50 meters is. So if I take 50 and multiply it by a fourth, what I'm going to get is 12.5. Okay, so it's going to be from 0 all the way to 12.5. Okay, now the force due to the cable. Okay, so if we look at the cable, that's going to be this guy. So 245 minus 4.9x. And then plus the force due to the load, which in this case is 1,470 dx. All right, so let's go ahead and clean this up. It's going to be the integral from 0 to 12.5 of this guy and this guy is going to give me 1715 minus 4.9x dx. Now let's just take the antiderivative of this guy. So it's going to be 1715x minus 4.9x squared over 2 from 0 to 12.5. Okay, and when I put that, I'm going to have 1715 times 12.5 minus 4.9, 12.5 squared divided by 2. And this is going to be approximately equal to 21,054.69. This is going to be in joules. Okay, so that is going to be my answer for that particular problem. Okay, so now let's say, for example, you wanted to switch it up. Okay, let's say you wanted to switch this guy with the other guy. Okay, so if you wanted to do the same thing, it'll give you the same answer. The only reason is this is why I'd rather not do that, because if you do, here's the thing, the bucket, the cable, still 500, I'm sorry, still 50. Well, if you want to take this chunk, delta x, okay, oops, that looks like an A. If you want to take that chunk and you want to call this instead 50 minus xi and make the top part xi, well, of course, you can do that. Okay, so the cable is still going to be the same. It's still going to be 1470 because nothing really has happened. Oh, no. That's going to be for the load. So the load hasn't really changed. Load is still the same thing because of where did I put it? Okay, load is still the same. Okay, nothing has happened to that. Okay, the only thing that's going to change now is the cable. Okay, because now the cable is going to be equal to the mass, which in this case was 1/2 kilogram per meter. Okay, times xi now, because xi is now going to be what's left over. Okay, so what you're going to have is the following. So this was the force. So now the force here is going to be 1/2 times xi times 9.8, okay, which is going to give me 4.9 xi. Okay, so when you evaluate the integral, it's going to be the integral from 1470, which is the force due to the load, plus 4.9 x dx. Okay, so you might look at this and be like, wait, this was a little bit easier. But the thing is, we want it to be a fourth of the way down. Okay, so basically what you're doing is you're kind of setting your x-axis to be 0, okay, right here. And then you have to go all the way down this way, okay? Here is where it's increasing. So if this is 50, okay, how am I going to have a fourth of the way down? Well, it's not going to be from 0 to 12.5 because then what you're going to calculate is this part, 0 to 12.5. That's what you're going to calculate. And that's not what we want. What we want is the 50 minus the xi. So it's going to be 50 minus 12.5. Okay, so 50 minus 12.5 is going to give me 37.5. So my integral is going to be from 37.5 all the way to 50. Okay, so because you have this additional thing that you have to worry about, it's going to be a little trickier, and you actually will end up with the same answer. You can just do that on your own, that you actually will get the same exact thing. But usually with these problems, I would rather do this part. Do something like this where you do not change these guys, because then if I set my 0 on the bottom, it's really easy for me to just figure out what x is. Okay, but it will give you the same answer, but it just really depends on how you want to address your distance. So if you felt very content with the first way that you did the problem, then do it this way. You don't need to do it the second way. If you want to make your life a little bit more complicated, then you can do it this way as well, but you'll still get the same answer.